let's work through these example problems of trigonometric integrals. If you haven't worked on these problems on your own, I highly recommend you pause this video and try them for yourself first, and only watch me working through these solutions if you get stuck so that you can't make progress on your own. So hopefully you've had a chance to work on this first example for yourself. Let's see what we get. So for this one, since both sine and cosine have odd powers, we can do either U substitution, either with sine or cosine. I would rather keep a cosine for a U substitution and turn the rest into sines, just because, I don't know, that's how I feel today. So let's write this as integral from 0 to pi over 2 sine to the 7th theta times, so I'm going to break this into cosine to the 4th times cosine. So cosine to the 4th is cosine squared squared. So that's cosine squared is 1/2, I'm sorry, that's not the identity I want to be using. Cosine to the 4th is cosine squared squared. Cosine squared is 1 minus sine squared theta, so that's squared, times, now we have a cosine left over, d theta. Okay. And now we can do a U substitution. So U is sine. U is sine theta. Du is cosine theta, d theta. So this integral turns into, let's see, when theta is 0, sine of 0 is 0, so U is 0. When theta is pi over 2, sine of pi over 2 is 1, so U is 1. All right. Now we do our U substitution, so sine is U, so U to the 7th times 1 minus U squared, and then cosine theta d theta, that's all du. Now we're going to need to multiply this out, so integral from 0 to 1, U to the 7th times 1 minus 2U squared plus U to the 4th, I guess, du. And then, let's see, integral from 0 to 1, U to the 7th times minus 2U to the 9th plus U to the 11th du. All right, so big powers, but we're still in polynomial land, so we can integrate 1 over 8 U to the 8th minus 2 over 10, so a 5th, U to the 10th plus 1 over 12 U to the 12th. And we're going from 0 to 1. Since this is a polynomial with no constant term, when we plug in 0, we get 0. So let's plug in 1. We get 1 over 8 minus 1 over 5 plus 1 over 12. So whatever that comes out to be, I'll let you work out that fraction arithmetic on your own. I think it's something like 1 over 120 or something. Okay. So if you haven't worked on number 2, pause the video now before I work on it. Okay, let's have a look at number 2. Just the integral of tangent squared. Well, let's see, there's no obvious antiderivative here, but remember with a Pythagorean identity, we can turn even powers of tangent into even powers of secant. So we'll get secant squared out of this if we use that Pythagorean identity. And we do know the integral of secant squared. It's tangent. So that sounds like a plan. So let's use the Pythagorean identity to turn tangent squared into secant squared x minus 1 dx. And now we can integrate straight away. So secant squared is the derivative of tangent, so the antiderivative of secant squared is tangent, minus, and then antiderivative of 1 is x plus a constant. And we're done. That one wasn't too bad. So have a look at number 3 before you watch my solution. Okay. How about tangent to the 4th, secant to the 6th. So let's see. these powers are both even. So if I take 4 factors of secant and turn them into tangents, I'll be left with 2 factors of secant. And then I'm set up for a U substitution using tangent. That sounds like a plan. So tangent to the 4th theta, I'm going to take 4 factors of secant, set those aside. That leaves 2 factors of secant, which we're going to use for our U substitution for du. We need to turn everything into everything else except these 2 factors of secant into tangents. So let's see, tangent to the 4th theta. Using that Pythagorean identity, right? Secant to the 4th is secant squared squared. Secant squared is tangent squared plus 1, so that's squared, times secant squared theta d theta. Now we can do our U substitution. So U is tangent theta, du is secant squared theta d theta. And we get integral of U to the 4th times U squared plus 1 squared times du. Now we need to multiply everything out. So we get integral of, let's see, U squared squared U to the 4th times another U to the 4th U to the 8th plus cross terms in the square give us 2U squared times U to the 4th is 2U to the 6th plus U to the 4th. Okay. So if you need to fill in the gaps in the algebra, write that out for yourself. But you'll get this when you multiply everything out, I think, unless I made a silly mistake. Now we can integrate term by term. So 1 over 9 U to the 9th plus 2 over 7 U to the 7th plus 1/5 U to the 5th plus a constant. And now we need to undo our U substitution. So 1 over 9 tangent to the 9th theta plus 2 over 7 tangent to the 7th theta plus 1 over 5 U to the, sorry, not U, tangent to the 5th theta plus a constant. And finally, we're done. All right, so pause the video and work on number 4. Okay, here's number 4, tangent cubed times secant. So both of these are odd. Since both are odd, I can set aside one factor of, tangent and one factor of secant. I have an even number of tangents left that I can turn into secants, and then I'm set up for my secant U substitution. Okay, that sounds like a plan. So let's see. Turn these the tangent squared into secants. Tangent squared is secant squared x minus 1 times tangent x secant x dx. Now we can do a U substitution where U is secant x, du is then secant x tangent x dx. So doing our U substitution, we get the integral of U squared minus 1 times du. So we get 1/3 U cubed minus U plus a constant, and then undo the substitution, 1/3 secant cubed x minus secant x plus a constant. All right, that wasn't that bad. All right, pause the video and try number 5. Okay, so for number 5, other than our Pythagorean identities and double angle identities, there are some other identities that come in handy sometimes, and here's 3 of them. These are called the product to sum identities. because they turn products of sines and cosines into sums or differences of sines and cosines, so hence the term product to sum. And it turns out that in physics, especially when you're working with waves, having products of sine and cosine is extremely common. Having products of sines and cosines that with different things inside is very common, because waves with different frequencies will all have, right, you'll have some sort of frequency times t, and you might be combining waves that have different frequencies, in which case you might be doing exactly this sort of thing. So with that in mind, let's see if we can work these out. So integral from minus pi to pi of sine of mx times cosine of nx dx. So here I'm asking you to verify that this gives us 0. So let's just work out this integral and see if we get 0. So since I have this whole setup with the product to sum identities, I hope that your first idea is to use the product to sum identity here. So this product to sum identity for a sine times a cosine is this first one. So 1/2 sine of the difference of these two. So it's the one inside sine minus the one inside cosine. So it's this one minus that one. So mx minus nx plus sine of the sum of the two. So mx plus nx dx. Okay. The stuff inside of our trig functions here, we can simplify those. So let's move the 1/2 outside. 1/2 integral from minus pi to pi of sine of, let's see, this is m minus n times x plus sine of m plus n times x dx. And now we can integrate, right? Now, the thing to remember about this is that m and n are constants, right? They're positive integers. So when we do this integral, x is the variable here. M and n are both constants. So when we integrate, let's see, I'm kind of running out of room, so let me go over here. We get 1/2. So integral of the first term is 1 over m minus n times, I guess I get a minus sign and a cosine cosine m minus n times x minus 1 over m plus n times cosine m plus n times x. Okay, my brain froze there for a second. And we're going from minus pi to pi. Okay, so let's see, 1/2 minus 1 over m minus n. So when we plug in pi, right, m and n are both integers, right? That's part of the setup here. M and n are integers, so cosine at an integer multiple of pi is going to be either plus or minus 1. So yeah, so this is cosine. For now I'm just going to leave this m minus n times pi. Okay, minus 1 over m plus n times cosine m plus n times pi minus, and then we get exactly the same thing but with a minus sign inside here instead of a minus pi in here instead of plus pi. So I'm just going to write this, I guess, with minus pi. Okay, so it's exactly the same except it's minus pi instead of plus pi. But remember that cosine is an even function. So if this minus sign inside of our cosines doesn't actually matter. Cosine doesn't notice it really. So we can just forget about it since cosine is even. But now the stuff inside these two sets of these two brackets are exactly equal, except they're being subtracted. And so everything cancels out and you just get 0. Okay, so we do get 0 by the skin of our teeth here. One thing that you might worry about is, well, we got these denominators, right? We got these m minus n in the denominators, and m and n are constants. They're integers, positive integers. But what if one of these things comes out to be 0? Well, m and n are positive integers, so this denominator can't be 0 since it's a positive integer plus a positive integer. But what if m and n are the same? If m and n are the same, then this denominator is 0, and none of this calculation makes sense. Well, if m and n are the same, this integral was actually the integral of sine mx times cosine, not n, but if m and n are the same, then we can put m here as well. And now the angle that's in both of these trig functions is the same. And then, so now you could use a double angle formula or use substitution straight away to calculate this antiderivative. So in the rare case where m and n are equal, there's actually a different trick that will let us calculate the integral. If we do that trick for the case where m and n are equal, you do still get 0. Okay, so let's try number B, letter B. So this is very similar, except this time it's both sine functions. Right? And there's two cases. There's the case where m and n are different, and there's the case where m and n are the same. So let's do the case where m and n are different. I'll let you do the case where m and n are the same. If m and n are the same, then replace n with m, and then calculate the integral, which you'll be able to do using a trig identity. But for the case where they're different, so integral from minus pi to pi. Of course, if m and n are different, then we can't use a double angle identity because these angles are different. But we can use this product to sum idea still. So we're going to be using this second product to sum identity where we have sine and sine in both of these. So we're going to get 1/2 cosine of the difference of the two, so mx minus nx. And from part A, we know that we're going to need to factor out the x. So let's do that now. Okay, minus cosine of the sum of these two. And again, we're going to factor out the x. So m plus n times x dx. Okay, move that 1/2 outside the integral. Now we can integrate this term by term. So integral of cosine m minus n is 1 over m minus n times sine of m minus n times x minus 1 over m plus n times sine of m plus n times x. And we're going from minus pi to pi. Okay. So we get 1/2 1 over m minus n sine of m minus n times pi minus 1 over m plus n times sine of m plus n times pi. Okay. And the thing about sine is right? We're going to get something very similar in this second set of parentheses, but the thing about sine is at every integer multiple of pi, sine produces 0. So every piece in this whole thing gives us 0. So we get 0, and we're done. All right, that one was a little easier than part A. Okay, and again, I'll let you do the case where m and n are equal yourself. Instead of using a product to sum identity, you're going to end up using some sort of double angle identity. All right, finally for part C, cosine times a cosine. So we'll use this third version of the product to sum identities. So let's see. Again, if m and n are equal to each other, you don't get 0, you get pi, which I'll let you work out yourself, just like with part B. And I'll work out just the case where m is not equal to n. So in that case, we need to use the product to sum identity. So we know we're going to get a half, so let's move that outside the integral. Integral from minus pi to plus pi, and then the rest of the identity is cosine of the difference plus cosine of the sum. Okay, so cosine of the difference, so m minus n times x, plus cosine of the sum, so m plus n times x dx. All right, and then integrate 1/2 times 1 over m minus n sine m minus n times x plus sine, 1 over m plus n sine m plus n times x. And this is all evaluated from minus pi to pi. And then just like in part B, when you have an integer multiple of pi inside of your sines, you always get 0, so this whole thing comes out to be 0. All right. So this whole thing with these product to sum identities might seem a bit academic. It's sort of amusing, I guess, that so many of them come out to be 0. But at first glance, it seems like it's just an amusement. It doesn't actually seem important. But it actually is important that it's important that the integral over one period, right, from minus pi to pi, of any product of sines and cosines gives you 0. That's actually very important because it's these results that make a whole field of signal analysis work, called Fourier analysis. Because these products come out to be 0, it lets you decompose any periodic signal into a sum of sines with different frequencies, with different values in here for m. So if these integrals didn't come out to be 0, a lot of our signal analysis mathematics that makes so much of our modern communication infrastructure work would fail, and we'd have to figure out some other way to do it all. So these are actually pretty important results.